Hello everybody and welcome to this A-level chemistry video about balanced symbol and ionic equations. And in this video we'll take a look at balancing equations, which won't be very different from GCSE level, but the equations will be a little bit more difficult. We'll have a recap of state symbols and what they mean, and then we'll have a look at formulae of ionic compounds before moving on to ionic equations and some examples of ionic equations like precipitation reactions. Now, before I start this, I should say that I will be aiming this at A-level chemists. Now, if you feel that balancing equations was something that you struggled with at GCSE level, I do actually have a GCSE balancing equations video that maybe you could check out first. Now, chemical equations show what happens during a reaction. It shows the reactants on the left-hand side turning into the products, and that arrow is showing a turning into. It is not an equal sign. And word equations just show the names of the reactants and the products. For instance, we've got here hydrogen and oxygen turning into water, whereas symbol equations show not only the formulae of the chemicals involved, but also what's called the stoichiometry. And what that means is how many of each of the chemicals are reacting together. So for instance, in this symbol equation, we can see that we've got two molecules of hydrogen reacting with one molecule of oxygen to make two molecules of water. And so at GCSE, you might have called these numbers multipliers, and that's still actually totally fine, but their technical term is the stoichiometric coefficient. And the stoichiometric relationship between these chemicals is that two of the hydrogen reacts with one of the oxygen. And this is a really powerful piece of information that we can use in the future. And we'll look at this in even greater depth in our reacting mass and limiting reagent video at a later date. So before we take a look at balancing equations, it's really important to understand why they need to be balanced at all. And the reason is that atoms can't be created or destroyed. And this is called the law of conservation of mass. Now, they can only be reorganized, and what that means is we can change how they are bonded together. And so, as a consequence of that, what we need to recognize is that you need to have the same number of each type of atom on both sides of the equation, because we can't be destroying atoms or creating atoms. So for instance, in this equation here, we've got one magnesium on the left-hand side and we've got one on the right. So we're obeying the law of conservation of mass here. We've got one hydrogen in the reactants, we've got two in the products, so we've just created a hydrogen atom. We've got one chlorine atom in the reactants, and we've got two in the products. So again, we've created a second chlorine atom. So we're breaking the law of conservation of mass, which is why this equation needs us to actively balance it. Now, this example isn't very difficult to balance, but let's just go through the rules of how we balance. So first of all, you might be given the question as a sentence even, and so you might have to write the word equation first. And then from the word equation, you will need to work out what the formulae are. You might be given some of them in the question, but not all of them. From there, once you've got the correct formulae in an equation, you need to work out how many of each atom you've got on both sides of the equation. And so that's doing the tally like I did before. And then you need to look at what it is that needs to be changed, and change the simplest thing first. And by that I mean change the thing that appears in the fewest number of formulae, so the element that is only on each side once. And so typically things like oxygen might appear in lots of different places, and so we should leave that towards the end. When we are trying to get the same numbers on each side of the equation, we need to look for a lowest common multiple. So typically if you've got two of something on one side and three of another, the common multiple being 6, we're looking to put our coefficients in to make the numbers equal 6. So you solve one problem and then you look to see if you've caused another problem. And if you haven't, then you keep working through until there are no more problems to solve and you've got the same atoms on both sides of the equation. So for my example up here, this is really quite straightforward to solve because our issue was the hydrogen and the chlorine. Remember that 2 belongs to the chlorine but not the magnesium. And so to make it so that we've got 2 chlorine on both sides, we just put the coefficient 2 in here. and that 2 multiplies both of these elements that come after it by 2, so we now have 2 hydrogen and 2 chlorine, which in fact is what we needed. Hydrogen, hydrogen, sorted, chlorine, chlorine, sorted. Now the one thing that you cannot do, or the biggest temptation at least, that you want to do but you can't, is you cannot change the formula. HCl is the formula for hydrogen chloride or hydrochloric acid. If you start messing around with that formula and make it HCl2, you've changed what it is. So that is the absolute one unbreakable rule. You cannot mess with any of the formulae at all. I suggest you just pause the screen here and have a go at these for yourself, and then I will work through them reasonably quickly because I want to get on to the ionic equations. So hopefully you've had a chance to have a go at these. This first one, the issue, if we do our tally, 1 aluminium, 2 oxygen, 3 oxygen. So in fact, there's problems with everything. Now we could easily solve the problem by putting a 2 in here, but actually that doesn't solve the most difficult problem, which as I say is often the oxygen. And so we've got 2 oxygen here and 3 oxygen here. The common multiple of 2 and 3 is 6. And so to make 6, we need to put a 3 in front of this oxygen, and that gives us our 6 oxygen here, and we need to put a 2 here, which gives us 6 oxygen in the product as well. Now though, we no longer have 2 aluminium, we've actually got 4 in the products because we had 2 in Al2, and 2 lots of 2 is of course 4. So we solve this by putting a 4 here. In the second one, 1 calcium, 2 chlorine on the right, 1 on the left, 2 hydrogen on the right, 1, 2, 3 on the left. Let's put the tally in this place over here. We've got 3 hydrogen here, 2 oxygen here, and 1 oxygen there. So to solve this problem, we don't need to touch the calcium, but if we do, whatever we put in front in these spaces has to be the same because we've got 1 calcium in each of these molecules. I would say that solving the oxygen problem is the easiest here. So we've got 2 oxygen on the left, 1 oxygen on the right. Put a 2 in here, we've now got 2 and we've got 2. So oxygen is sorted as well, and calcium is already sorted. Hydrogen now in the products, we've got 4, and hydrogen in the reactants, we've got 3. So to solve this problem, we need to put a 2 in front of that hydrogen, and that gives us 2 hydrogen here and the 2 hydrogen that we already had over there. Remember, I meant to say this before, but remember when you're dealing with brackets, that 2 means 2 of everything inside the brackets. So 2 oxygen and 2 hydrogen, even though it looks like there's only 1 of each inside the brackets, outside of the brackets solves that for us and multiplies it. And so now 4 hydrogen on both sides, we're now sorted. 2 multiplied by 1 gives us 2 chlorine, and we already had 2 chlorine, so that is sorted as well. So the correct numbers to balance this were the 2 and the 2. This third one looks tricky, but it's actually pretty straightforward. The one thing to do is to just decide which problem to solve first. So if you dived straight in and solved your fluorine problem, let's do that. We have got 2 fluorine here, and we've got 6 over here. And we could put a 3 in front of here, and then that would give us 6 and 6. But then if we move on to solve our sulfur problem, we've got 8 sulfur in the reactants and only 1 in the product, so we definitely need an 8 here. And whatever numbers we have here and here, the number in the products has got to be 8 times bigger. So 8 multiplied by 6 is 48. So we've actually got 48 fluorines in our products, which means we need 48 over here. And so we actually need 24 fluorine here. There's nothing wrong with having a go and getting the numbers wrong first of all, provided it's really clear what your final answer is. And then this last one, 4 carbons, 1 carbon, so we need a 4 in front of the carbon dioxide, 8 hydrogen, that's 8 hydrogen and only 2 hydrogen, so we need a 4 in front of the water here. And so then in terms of checking our oxygen, we've got 8 oxygen here because 4 multiplied by 2, and then we've got another 4 over here, so 8 and 4 gives us 12 oxygen in the products. So we need 6 in the reactants, 6 lots of O2, because 6 times by 2 equals 12. Now I just wanted to do one more example that involves oxygen, just to raise an issue that it is okay to have fractions in equations if we need them. So here's an example of what I mean. It looks exactly the same as the previous one, except we've got more hydrogen in the reactants. So we've got 4 carbon, so we need a 4 over here. We've got 10 hydrogen, so we need a 5 in the water over here. And so now we've got 8 oxygen in the CO2, and we've got 5 oxygen in the water. So 8 and 5 gives us 13 this time instead of 12. And so therefore we need 13 oxygen here. So what do you multiply by 2 to get 13? Well, the answer is 6.5. And so you can put 6.5 O2, or you can put 13 over 2 O2. That's absolutely fine. Alternatively, you could just double everything. If fractions leaves you a little bit uncomfortable in balanced equations, you could just double everything, and then we would only have integers in this equation. And so our equation would look like this. And in fact, it's not the case that one of these is better than the other. You could write any of these 3 and you would get the marks in just the same way. Before we move on to ionic equations, we need to take a quick look at formulae because they become central in ionic equations. So first of all, I want to say something about metals. All metals go around by themselves. There is never ever a little subscript after the symbol for an element when it is in its pure form. So aluminium is just Al. Magnesium is always just Mg, iron Fe. So when it is the pure element, there is nothing after it. It is just the symbol and then whatever state it might be. Non-metals, they can vary. There are a number of elements that are diatomic molecules, and the way I remember that is I have no obviously brainy close friends, and that tells you the symbol of each of the elements that exists as a diatomic molecule. That's called a mnemonic, where the first letter of the word that you're remembering tells you something else. So that's the symbol of the non-metals that go around in pairs. Now, as you go through the course, you will work out that there are a few other non-metals that exist as molecules, such as sulfur and phosphorus. But otherwise, if you're not told any different, carbon, for instance, is just an element by itself with no numbers, so just C. Where it gets more complicated is the ionic substances, and you have to work out what the formulae are for these ionic substances by reminding yourselves about how the charge of the ion is connected to the position in the periodic table. And for most of the periodic table, this is really straightforward and is linked simply to the group number. So for instance, the elements in group 1 have got 1 valence electron. That means they've got 1 electron in their outer shell. And to complete their shell, what they do is they lose an electron. So they lose an electron, and so that means their ion charge is going to be positive. For group 2, it's the same principle, 2 electrons in the outer shell. So they have got 2 valence electrons. They need to lose those 2 electrons, and so then they become a 2+ ion. The row to just take particular care on is here. What I'm saying in this row is what needs to happen to their valence electrons, and they need to lose 2 electrons here. For group 3, it's 3 electrons in the outer shell, so they need to lose 3 electrons, and then they become a 3+ ion once they've done that. Now, group 4 often doesn't bond ionically, so we'll leave group 4 and we'll move on to group 5. With 5 valence electrons, they need to gain 3 electrons, and that makes them a 3- ion, because remember, electrons are negatively charged. That's something I should have said and reminded you about earlier. Group 6 has got 6 valence electrons. To get a full shell, they gain 2 to become 2- as an ion, and then group 7 is 7 electrons, gaining 1, and becomes a 1- ion to get a full shell. Group 0 generally does not form ions on here, and this is because they already have a full outer shell of electrons, the full energy level, and so they don't need to form any bonds to anything. Last of all, the transition metals. Now, one of the characteristics of a transition metal is that their oxidation state can vary, or that's a slightly more technical way of referring to the charge that it has as an ion, and that will simplify for now. So, for instance, iron here can be iron 2+, or it can be iron 3+, and it can vary. But the good news is that for transition metals, where there is variety, they will give you a clue in the name. So it will say iron 3 chloride or iron 2 sulfate in Roman numerals, and you just need to be adept at looking for that and noting that that Roman numeral means the size of the positive charge on the metal. Now, there are a few ions that are not single elements, so it's a little bit harder to work out what their charges are. And so I'd probably recommend that you just remember these charges. You can actually work them out by using a combination of electronegativity knowledge and redox, but it's probably easiest just to remember the charges and the formulae of these ions by themselves. So for instance, the ammonium ion contains nitrogen and hydrogen, and that's got a 1+. You don't need to write the 1, it just gets rid of any doubt. The hydroxide is 1-. The nitrate is NO3, 1-. Sulfate, SO4, 2-. Carbonate, CO3, 2-. And phosphate, PO4, 3-. As I say, I suggest you remember these. I'll just give you one example of how we could work out what it would be. So oxygen from the periodic table, we would expect that to be a 2- ion, and hydrogen we would expect to be a 1+ ion. If you sum those two numbers together, 2- add 1, we do get 1- overall. So there is definitely logic there. It's just probably easier to remember the formula than work it out. When you're working out what the formula of an ionic compound is, it's really important to be clear about why something has a formula at all. And the reason it has a formula is because the elements that have transferred electrons between each other have done so in such a way that they all have got a complete shell of electrons afterwards, which means that if one element is losing electrons, another element is gaining electrons. And so because that's the case, the total positive charge after bonding must be equal to the total negative charge after bonding. Otherwise, electron transfer wouldn't have been equal. And that's one method of writing out a formula. So for instance, when magnesium bonds to chlorine, it gives away 2 of its electrons and becomes a 2+ ion. But chlorine, when it becomes chloride, only needs to gain 1 electron. So that can't possibly be the case. So what that means is a second chlorine is needed to gain that other electron that magnesium is throwing away. And so the formula must be MgCl2. And in the same way, if we have the element sodium in group 1, it forms a 1+ ion by giving away 1 electron. If it's bonding to oxygen, oxygen needs to take 2. Well, it can't take both of those electrons from one sodium because the sodium is only giving away 1 electron. So we need a second sodium to give away its electron to the oxygen. And so the formula is Na2O. And in the same way, aluminium 3+ has given away 3 electrons. Oxygen, forming the oxide 2-, has only taken 2. So we need to have it so that the aluminium and the oxide are equal. And so this is back to our lowest common multiple, which is 6. We need to have 6 electrons being lost and 6 electrons being gained. And so the formula is Al2O3. And you do this for molecular ions as well. So if we've got iron 3+ and we've got hydroxide 1-, we need to make sure the positive and negatives are equal. So that means we need 3 of our hydroxide ions. And when we write the formula for this, remember, we need the brackets around our molecular ion and a little 3 after it. So the only time that you need brackets is if you've got more than one of these molecular ions, and that's an ion made from more than one element. The second method of working out a formula is probably easier. I don't like it as much because you can just do it with a simple method, and this method is swap, drop and simplify. And so the idea here is if we take potassium and oxide as ions, what you do is you swap the size of the charge over. So potassium is 1+ and oxide is 2-, so you swap those numbers over and then you drop them down onto the line and we end up with our formula K2O. Let's do that again with the zinc. So you swap the 2 plus of the zinc for the 3 of the nitrogen, so it becomes a 3 over here, and that becomes a 2. Then you drop it down onto the line, and we get Zn3N2. So this is definitely faster. We swap the 2 from the calcium over to the nitrate, and the 1 from the nitrate comes over to the calcium, so we get Ca1, we don't bother writing ones of course, and then NO3, 2. Now we don't write it and leave it like that because that looks like there's 32 oxygen, so we need our brackets around our molecular ion. And just to do a few more of these, swap, drop and simplify. So we swap the 2 from the copper over to the 2 of the sulfur and vice versa. We drop it down onto the line, Cu2S2. And the reason why we've got simplify is that these are ionic formulae. It doesn't mean 2 copper bonded to 2 sulfur. This is the ratio that they combine in the ionic substance. So 2 to 2 is the same as 1 to 1. There'll be billions of copper and billions of sulfur, but they are present in a 1 to 1 ratio, and that's why we need to swap, drop and simplify. These last two, that 1 becomes a 2 and the 2 becomes a 1 because we've swapped them. We drop them down to the line, so we've got NH4 2 CO3 1. Don't bother writing the 1. We need brackets around the ammonium, otherwise it looks like 42 hydrogen. This last one is as hard as it can be really. We swap the 3 for a 2, and then we drop the 2 down onto the line, Al2 SO4 3, and as before we need brackets around the SO4. And that's working out formulae the quick way, swap, drop and simplify. And simplify is only necessary if the two numbers are identical, 2 to 2 or somehow 3 to 3. And remember, we don't show ones. Just a quick reminder here about state symbols. There are 4 state symbols that you need to know. SLG for solid, liquid and gas, and AQ for aqueous solution. So these are all lowercase letters, don't get confused and write a capital, and they're all pretty self-explanatory, except perhaps the aqueous solution, and I want to explore solutions a little bit now as a way into ionic equations. Now, I hope you remember that a solution is made when a solute is dissolved in a solvent. Now, solute doesn't have to be a solid. It probably most commonly is a solid, but you can dissolve one liquid in another, and the substance that does the dissolving is the solvent, and you make a solution. So, for instance, we could have dissolved copper sulfate solid in our water and made copper sulfate solution. And the absolutely crucial thing to clarify about ionic substances, when they dissolve in water, they are no longer bonded together. So the copper and the sulfate are no longer attracted to each other at all when they're bonded. What happens is the water molecules in the solvent pulls the ionic lattice apart, and so the copper and the sulfate, their electrostatic attraction that was holding them together, that's been broken, and new attractions have formed between the copper and the water, and the sulfate and the water. Specifically, it's because water is a polar solvent, and the slightly positive hydrogen is attracted to the negative sulfate ion, and the slightly negative oxygen from the water is attracted to the copper. And so the new attractions that have been formed are such that they produce enough energy to break apart more of these copper and sulfate ions. And so crucially, once a solution has been formed, the copper and the sulfate that were attracted to each other in a solid are completely separated now, and they're moving around with no attraction between them at all. And let's be clear, this is the case for all aqueous ionic substances. The ionic substance falls apart into its component ions. It doesn't fall apart fully. The sulfate is still sulfur and 4 oxygen joined together, so it doesn't fall apart into its elements, it falls apart into its ions. So why does this information matter? Well, it helps us to understand more clearly what's happening in a chemical reaction. And this is how we link into ionic equations, because ionic equations allow you to simplify a full chemical equation by actually only considering the ions that react. And so sometimes there are ions that are there that don't take part in a chemical reaction. And for instance, when hydrochloric acid reacts with sodium hydroxide, we make sodium chloride and we make water. But at the beginning, in the reactants, in one reactant we've got hydrogen ions and chloride ions spread out in the water, and in the sodium hydroxide we've got sodium ions and hydroxide ions spread out in the water because they're both aqueous solutions, they're both dissolved in water. And then when we mix them together to make our products, because sodium chloride is still aqueous, it will still have sodium ions and chloride ions spread out in the water. And so they haven't actually changed. They were present, but they didn't really take part in what had happened. And so we can reduce this situation down to focus in on the ions that are actually reacting. The hydrogen ions that were present at the beginning and the hydroxide ions that were present at the beginning, they are changing, they're combining to make the water. But the sodium ions and the chloride ions, they were there at the beginning and they were there at the end. And so they have just watched this reaction unfold without actually changing. And we call these spectator ions because they didn't take part in the chemical reaction. It's a little bit silly, but it's a bit like chemical equations being recipes. And so you take some flour, some sugar, some margarine and some rice out of your cupboard and you make some cupcakes. And at the end, you've got some cupcakes and you've still got your rice because you wouldn't put the rice in the cupcakes. And so that means that the rice was there, but it didn't take part and it didn't change. And so you wouldn't include that in the recipe because it's not actually being used. And so you only include in the chemical equation those chemicals that are actually changing, not the ones that are there but not changing. And that's where these spectator ions are relevant. So if you had been asked to simplify this full chemical equation that we've got up here in black into its ionic equation, you would eliminate the spectator ions. So you would get rid of the chemicals that aren't changing. So that's the chloride because it's there at the start and the end. And the sodium is there at the start and the end. And so we reduce it down to what is actually changing, which is the aqueous hydrogen ions because they're reacting with the hydroxide ions to make water. And this is in fact what all acid plus hydroxide reactions will reduce down to. So suppose you have been presented with this symbol equation and you've been asked to reduce it down to an ionic equation. What are the steps that we need to go through? Well, first of all, remember that ionic equations really focus in on the aqueous solutions that are ionic. And so anything that is not an ionic aqueous solution won't change at all from the full chemical equation. So rule 1 is to rewrite everything that is solid, liquid or gas exactly how it is before. And that will be present exactly like this in the final answer. Rule 2 is to split apart the aqueous substances that are ionic into their component ions. So in our example here, copper sulfate splits into copper and sulfate, and so does zinc, and sulfate splits into zinc sulfate. Now, because I've remembered that sulfate is a 2- ion, then I know that copper must be a 2+ ion, because the positives and the negatives have got to cancel each other out. And that's the same with the zinc. Rule 3 gets us to look for spectator ions. We look for spectator ions and we chop them out. We remove them from the overall equation. And then the final rule, rule 4, is to write down the ions that are changing along with any of the solid, liquid and gases that obviously don't change, it's just the aqueous solutions. Don't forget to include state symbols for everything in your final answer. It's particularly common for people to drop the AQ for the ions that they've worked out. And finally, we have written our answer now, but it's a good habit to get into to think of one last rule, which is to check the charges on both sides of the equation, because as with GCSE level, we of course need to balance for our atoms, but now at A level we need to get more adept at checking for charges as well. So we've got 2+ charge on the left-hand side from the copper, 2+ charge on the right-hand side for the zinc, and so we can be confident that this equation is balanced in terms of charge as well as for atoms. Right, well, we're going to finish off this video with just 4 more examples of ionic equations. Feel free to pause it now, have a go at it yourself, or you can just listen to me going through the model answers. So the first one is very similar to the previous example. That's a precipitation reaction where we end up making a solid, which is of course called a precipitate in a precipitation reaction. So remember, rule 1, we will rewrite our substances that are solids, liquids or gases exactly as they appeared in the original equation that we were simplifying down to an ionic equation. Then we will look at the aqueous ionic substances, and we've got Fe2+ and SO4 2-, and we've got Mg2+ and SO4 2-. Rule 3 is to look for the spectator ions, so ions that are present at the beginning and ions present at the end. And on this occasion there is one spectator ion, which is the sulfate, present at the beginning and at the end. And then rule 4 is to write in the ions that are changing, including the state symbol, so Fe2+ is turning into Mg2+, aqueous plus Fe. Now you will get adept at spotting where the spectator ions are without having to do this step that I've done in red. And we can do that just by looking at the equation here. We've got aqueous silver at the beginning, solid silver at the end. So the silver is definitely changing. And so we can write our answer with the AgCl, of course, at the end. And then all the reactants are aqueous at the beginning. But we've got aqueous nitrate at the beginning and we've got aqueous nitrate at the end. So we can chop out the nitrate without actually writing the spectator ions at all. However, it is sometimes helpful to write out the ions in full, because what that allows you to do is it allows you to think, okay, nitrate is a 1- ion, which means that silver must be a 1+ ion. So let's write the silver 1+ in here. And then we can see that K is a 1+ ion and nitrate is a 1- ion. And we can see that nitrate is a spectator ion when we've done this. So some people will like to do it just by inspection. Some people will want to write out the ions themselves. And for potassium chloride, potassium group 1 is 1+, chloride group 7 is 1-. We've got potassium at the beginning, potassium at the end. So we have two spectator ions here, and the chloride is present in the actual overall ionic equation. Ag+ plus Cl- ions makes AgCl as our final answer. And for the third question, we can see that we've got barium sulfate solid at the end. Everything else is aqueous, so we can see that we have got these ions here. So it's really important to note that when you've got 2Cl, because chloride is an ion of a single element, we make 2 chloride ions. They don't go around as Cl2 anymore, they split apart into 2 chloride ions. And similarly, because in H2SO4 we've got single hydrogen ions, it makes 2 H+ and sulfate. And last of all thing to note is because we've got 2 HCl, we will have 2 hydrogen ions and 2 chloride ions. Now we've done this, we can look at what the spectator ions are. We can see that we've got chloride at the beginning and the end, hydrogen at the beginning and at the end, and so the ions that are changing are the barium ions and the sulfate ions, and so this is the overall ionic equation. Another way of looking at this is certainly when you've only got one product, you can look at what ions are present in the ionic solid, the precipitate. So we've got barium ions, of course, and we must have sulfate ions, of course, and it follows that these must be on the left in the reactants. It's not always easy to do that. If we have a look at this final example here, if we take the substances that are not aqueous, so that's our two products over here, water and carbon dioxide gas, and then split everything apart into its ions. Once again, being particularly careful because we had a 2 there after the Na, we need 2 Na+. Carbonate is a molecular ion. We've got 2 H's and we've got 2 nitrates, which is why we've got this here. And in the same way, we've got 2 sodium and we've got 2 nitrates here. And now we've got this, it's easy to see that we need to get rid of our sodium spectator ions and our nitrate spectator ions, and our final equation gets written CO3 2- plus 2H+ turns into water and carbon dioxide, and not forgetting the state symbols of aqueous for both of our ion reactants. So there you have it, ionic equations in a few simple steps, and you can even miss out one of the steps if you feel confident just inspecting the original equation and working out what the spectator ions must be from there. Okay, that's the end for this video. I hope it was useful. I'll see you again soon.